Okay, so we are trying to solve problem 21, chapter 6 of Halliday. Okay, so chapter 6, problem 21, Halliday ninth edition. Very well, so let's see what we have. We have a box full of sand that we are trying to pull across the floor. So here you have, let me make our drawing here. We have a box full of sand. We are trying to move it across this floor. Okay. And how are we going to do that? We attach a cable to this box. So here you have the cable, and this cable can hold a certain tension that cannot be larger than a certain value. So let me put here the tension force. This is tension, and the maximum value that this tension can be so that the cable doesn't break is 1100 newtons. Okay. The problem also tells us about the coefficient of static friction. So there is friction in this problem, and this coefficient of static friction is 0.35. So we know we have to take into account friction. The question is, what should be the angle between the cable and the horizontal? So here is the angle that we are asking. What is this angle theta? In order to put the greatest possible amount of sand. Greatest means maximum amount of sand that we can have in this box. So what is the angle for that? Okay. What is our main concern? Friction. When we are trying to pull this box full of sand, friction will prevent our motion. And the larger the amount of sand that we put, the larger will be the friction. Friction is related to normal force. Normal force is related to the weight of this box. Okay. And what is our main concern when we think about friction? So friction is our main concern, but which kind of friction? Well, our main concern is the static friction, because remember, the maximum static friction is even larger than the kinetic friction. So we can break our cable when we are still trying to overcome the maximum static friction. Okay, so we have to find out this optimal scenario so we don't break the cable once we have the maximum static friction. All right, so then the question is, what is this angle for maximum mass? Maximum mass angle, what are we after? An equation that connects mass with angle, an equation that will allow us to look for the derivative of the mass with respect to the angle. So then we can find this maximum point. Okay, so the idea is, if I would have a plot, a function for the mass with respect to the angle theta, there is some point where we get the maximum mass for a certain angle. That's this point that we are trying to find. And how we are going to reach that if we find an equation for the mass and then we do the derivative with respect to this angle equal to 0, that will give us this maximum point. That's what we are after. All right, so we have to write the equations. And again, I repeat, our main concern is static friction, because maximum static friction is even larger than kinetic friction. All right, so let's try to get to that equation connecting mass with angle. And well, to write that, we have to put all the forces into this problem. In addition to the tension, in addition to friction, we have the weight of this object, and we have normal force, always perpendicular to the surface. Very well. Let's go for the equations now. Let's choose a frame. I'm choosing positive to the right and positive up. All right. Starting with x direction. Sum of all the forces in the x direction equals to MAX. What are the forces in the x direction? We have the tension force, positive, but a component of the tension force, the component in the x direction, so cosine of theta. So I'm thinking here about this component here, which is adjacent to the angle, so cosine of theta. What else do we have in the x direction? The friction. The friction trying to break our cable if we are not careful enough. So which friction we are thinking about? The maximum static friction. Okay, anything else in the x direction? No, we are done. And this should be equal to 0 because of static friction, we are thinking about no motion yet. All right, very well. Now let's go and try to find, as we said, an equation that involves mass with angle. Well, I see angle here. I still don't see mass. But let's continue a little bit more. What is friction force? Friction force is that coefficient of static friction multiplied by Fn. Okay, equal to 0. And what is Fn? Well, to find Fn, I have to go to the equation in the y direction. Sum of all the forces in the y is MAy. What do we have in the y direction? We have Fn pointing up, so positive. What else do we have? Careful, we also have a component here of the tension force in the y direction, opposite to the angle, so that is going to be a sign. So we have here also plus Ft sine of theta. What else do we have in the y direction? Mg, but Mg is pointing down, so minus Mg, and this is equal to 0. No motion in the y direction. Okay, so with this, we found my Fn. It's Mg minus Ft sine of theta. Very good. Let's use this into this equation. So now we have Ft cosine of theta. Very good. Minus the coefficient of static friction. And now instead of Fn, I'm going to put everything that we found there, Mg minus Ft sine of theta. This is equal to 0. Okay, so now I see mass showing up in this story. Very good. I see angle. So what we want to do now is to write an equation for the mass as a function of angle. Okay, so what I'm going to do is I'm going to isolate the mass and put everything else that doesn't depend on mass on the other side. So here I have the coefficient of static friction, M and G. Okay, so think about this being on the right side. And what we have remaining, we have Ft cosine of theta, and we have, careful, this is minus and this is minus, we have plus coefficient Ft sine of theta. Okay, all right, so things are starting to look better and better. I'm going to isolate M, but before that, let me just show to you that here I can write things as Ft cosine of theta plus that coefficient and sine of theta. All right, okay, I'm isolating M, so I have M on this side equals to the coefficient and G down. Okay, so this is our equation. So let me just rewrite the same thing here. Mass is then the tension, this coefficient, and G. This is all numbers. Here we have what we care about, the angle, cosine of the angle, then number, the coefficient, and again, sine of theta. This is the equation that we arrived as we wanted, an equation for the mass as a function of the angle. Perfect. What we want, the maximum mass. How do we find maximum? Derivative. So the derivative of the mass with respect to the angle equal to 0. That's what we are going to do. So let me do this derivative of that equation. Well, don't need to touch Ft, this coefficient, G is just a constant. Inside we have cosine of theta. What is the cosine of theta? Minus. The derivative is minus. And then the coefficient. What is the derivative of sine? Well, that's cosine of theta. And this whole thing has to be 0. In other words, this thing here has to be 0. So let me write that. Minus sine of theta plus that coefficient cosine of theta has to be 0. Very well. So now things look very good. I'm going to say that sine of theta, sine of theta minus that coefficient cosine of theta is 0. So sine of theta has to be that coefficient of static friction cosine of theta. So I can put cosine here. I have sine divided by cosine equals to that coefficient. What is sine divided by cosine is tangent. Very good. And that coefficient. So that's the equation. That's the equation that will give us the optimal angle to get the largest mass. Okay. Once we put here this coefficient, which is 0.35 that is given to us, find then this angle, you will see that this angle is 19 degrees. We found what we wanted. So this is part A of the problem. Part B of the problem is, okay, now that you know the angle, find the mass. So for that, I come back to our equation for the mass. I come back here. What is it that I'm going to put in this equation? Well, the maximum tension force, which was that 1100 newtons. This coefficient 0.35, G is 9.8. Now here we have our cosine of 19 degrees. We have to find that. 0.35, then the sine of 19 degrees, and you're going to find this mass, and this mass is, the value of this mass is 340 kilograms, and that's the end of this problem.